Hello, everyone. My name is Sayed Mohsen Vazirizadeh, and I would like to thank you for joining us on this tutorial. I will talk about some of the most common forecasting models for spatial temporal prediction of incidents, in particular highway or traffic incidents. Emergency response management, DRM, has multiple components. In general, an accident happens, then it is reported usually through a 911 call. Then a human operator dispatches a unit to that incident. However, other components can be employed to improve the process. And please keep in mind, the main goal is we want to be on the scene as fast as possible. In a life-threatening situation, minutes or even seconds matter. And the focus of this presentation in particular would be incident prediction models, but Ayan later will talk about prediction and allocation later. So this is the general pipeline. So proactive managing of such a system requires an integrated pipeline of components. Let's briefly review them together. So the first part is we have to collect as much useful data as we can from the environment, including but not limited to historical incidents, traffic information, weather data, and the accuracy of an ML model or machine learning models heavily depends on that. Consequently, it's very crucial that we collect useful and high quality data for our model. Then we have detection. You may remember, like that was, I think, about 2 years ago, the cathedral in France, the Notre Dame, it caught fire. And actually, it was on social media platforms like Twitter or Instagram, and sooner than receiving an actual 911 call, which shows the power of social media and crowdsourced platforms that people post about it, and we receive, and we can see those posts sooner than receiving an actual and formal report. And some of you may be familiar with the Waze, the navigation platform. So one of the things actually we were working on it is using the crowdsourced platforms for detecting the incident. So Waze collect the data from the users, and it also evaluate the users based on their historical performance and reliability. So for example, we can use that data because users are reporting a time and location for incident. Also, our historical data is showing that location is like a dangerous location. And also, for example, we can see a traffic congestion in that location. So we can dispatch a responder even before receiving a 911 call if we are sure with specific threshold or value for uncertainty. So we can dispatch a responder even before receiving 911 call. So that would be, for example, one strategy for detection. The prediction would be the main focus of this presentation, that we are trying to use other features from the environment from the past to predict the location and the time of an incident. And then we have allocation and dispatching, which will be briefly mentioned later. So some of the challenges, Ayan mentioned in general the challenges for incident prediction, but in particular for highway and traffic incident prediction. The first part is collecting data. Many factors are involved in road accidents, which requires collecting various types of data from assorted resources with different resolution and quality. The process requires good infrastructures, strategic planning, and investment. For example, if you want to train a model based on 10 years of historical traffic data now, you would have needed to start collecting data 10 years ago, which includes installing the sensors, having a streaming pipeline, and reliable data storage or data lake to keep the data. Then usually data is coming from different organizations or different resources. So combining them may not be easy. Because of various reasons. A simple example can be assume you have the geometry of the roadways through OSM, for example, and you have the GPS of the accidents from another source, and this coordinates are usually noisy. And if the location that you want to focus is very packed, so mapping this incidents to the segments, considering the noise that we are facing, may not be very easy. And that was just one example, but any other source of information that data sets that you want to combine, you may see some of this type of challenges. Then this is the sparsity. Although frequency of road accidents is high when viewed from the perspective of total time and space, incidents are very rare. So for example, if I ask you what would be the chance of an accident in a roadway segment close to your home in the next hour or so, your answer will be possibly 0 or close to 0. But if you look at the data, you will see, for example, 10 accidents happen in your neighborhood in the last month. So it depends on the resolution that you're looking at. Sparsity can be a huge problem. And the next part is irregularity. So accidents are inherently random in nature in high spatial temporal resolution. There are multiple factors from roadway condition, type of the car, even the age of the driver, or other factors actually in drivers. And the combination of these factors can generate totally random events. Another thing is this pattern may change over the time. For example, autonomous vehicles can change the pattern of incidents. For example, rear-ended incident rates may change just due to level 1 autonomy. Or for example, COVID has changed the traffic pattern, and consequently it has changed the accident pattern as well. And the last one is the resolution. So while achieving a high resolution prediction is virtually impossible, reducing the resolution may cause aggregation bias and unobserved heterogeneity. Therefore, resolution level should be selected strategically and based on the application of the model. I will talk about some of the mathematical notations. As most of the machine learning methods, we are trying to choose a function to, for example, in this case, to predict a feature of incident, for example, the frequency or the likelihood of incident or the severity of incident, which here we show it with X. And we use the data that we collected from the environment, for example, temperature, traffic, weather, that we show it with W here, for example. And then we want to adjust the parameters of the model theta to reach the maximum performance or accuracy of the model, or minimize the error of the model. And usually the most important data that we need is the incident data. And for example, we can, depends on the range and the time range and the space range, we can have n samples of data, and usually they should have this main important features. First, the location of incident, which we show it with S, then the time of the incident or the time range of incident, and some other features regarding the incident. For example, K, which is the intensity, which comes directly from the incident, or W, which comes from the environment of the incident. For example, like temperature or traffic, or for example, we know in the morning, the chance of one type of incident might be higher than the afternoon. So W can include those type of features as well. And the models, so during the time, models has changed a lot, but a linear regression is one of the earliest models used for incident prediction. However, regression is inherently not designed for discrete and strictly positive outputs. So for example, if you want to predict the frequency of the accidents, it cannot be -1, and it should be always a positive value and usually integer. And to address this problem, Python models were used. So Python models in particular is designed for predicting that type of behavior, like integer and positive values. And in general, you can see the formulation here. So usually we are trying to predict the rate based on some other features. Python models in this type of definition is one of the GLM models. It is very simple. It is useful, but the main problem is it has some limitations. So for example, a Python model has the same value for the mean and the variance, which may not be the case when we're looking at the data. And this is called over dispersion or under dispersion. So when the variance exceeds the mean, we call it over dispersion, and the variance is less than the mean, we call it under dispersion. To address this problem, different types of Poisson models that were introduced. One of them is Poisson gamma distribution, which the main idea is the rate for the Poisson is following a gamma distribution. So for example, here in the first line, you see the formulation for a Poisson model. And so some people use it lambda, some people use it theta, which is lambda times t, and t is the time range of interest. And the main idea of Poisson is giving you the probability of observing n events during the time of t, while the rate of occurrence in that unit of time is lambda. And of course, you can replace lambda times t with theta. This will give you a PMF. So assume, and this is the definition of the gamma distribution. And gamma distribution will give you the PDF of observing alpha events in a specific time range. And if the theta here is following a gamma distribution, we call it Poisson gamma. And this one is showing the combination of them. The good thing about Poisson gamma is it has a closed form solution, as you can see it here, and they call it actually a negative binomial, which makes everything easier. So as I said, here, mean and variance for the Poisson model is the same, which doesn't have that flexibility, which is not the case for the negative binomial, which gives us more flexibility. But the point is, we are not just limited to gamma. We can choose almost any other distribution. So for example, we can use log normal distribution, which is still more flexible. But the main challenge is if you don't choose the distribution for the rate smartly, you may not get a good closed form solution for it. So that would be the catch. But I've seen recent papers that you're using inverse gamma distribution, which is even more flexible, and it can follow the trend of accidents even better. However, the main problem is if you want to have a closed form solution for it or not. These models are flexible, but usually accident rates in high spatial temporal resolution, they are very sparse. To address this problem, zero inflated model were introduced. So the main idea of zero ZIP models is having a dual states, one which is the normal state and the other one which is the zero state. And the excess of zeros cannot be explained by just a Poisson or just Poisson or log normal model. So you need something more flexible, in particular to address the excess number of zeros. So the way that a ZIP model works is first you have a logistic regression, which can be like a classification that if there is zero or not, and if there is not, then you can use a Poisson model to calculate the rate. So it has two phases. I think that would be a little bit easier if you use numbers to explain it. So assume this is my observation. I know 80% of the time there is no accident. 8% of the time there is 1, 4% there is 2, and so on. And this is the prediction of a ZIP model. But let's see how ZIP model gets to that value. First, it uses a logistic regression, and the logistic regression is telling us 77% of the time there is no accident, which is this part. This is a logistic regression for classification 0, for example. And 23% of the time, there is at least one incident. And in that 23% that you can see it here, which the logistic regression is telling us it's class 1 or class not 0, from that, then we can use the Poisson, and the Poisson model is telling us 14% of the time, it can be 0. So the summation of 77% and 1 minus 77% times 14%, it's going to give us this 80%. And for example, for calculating the rate 2, so I know 23% of the time it's not 0, and from that 23% of the time, 18% of the time is 4. So the multiplication gives us this 4% here. ZIP model are more flexible in terms of addressing the sparsity in the problem, keep tracking of excessive number of zeros in the problem. However, you need a lot of data because usually you use it when your data is very sparse and you're going to have a lot of zeros, but you want to have a lot of, for example, 1, 2, and 3 to enable the Poisson model be trained or to be adjusted. And furthermore, this is just an assumption that we have a mathematical assumption that we have a dual state, but in reality, that might not be a good assumption. And when we are looking at the data, we come up with that idea. But in nature, that might not be the case. Then we have the multi-level models. Many kinds of data, including accidents, they may come from different resources. So, for example, consider we want to predict the incidents, but we have the data, for example, from California, and also we have the data from Tennessee. Even though both of them are accident, even though, for example, rain can increase the chance of accident, but the trend might be different for various other reasons. And for example, the California here, you can see it in red, and the Tennessee, for example, you can see it in green. If you use just a simple regression, technically you're predicting the trend, not each of these. So what the multi-level is trying to do is trying to bring the effect of other parameters. So this one is a formulation of a simple regression, but in a multi-level regression, you consider this, but these parameters, they also follow a normal distribution. So which gives you the opportunity to have a random variable. For example, in this case, in my example, the random variable was about the region. So you can have a random variable for the region. So you may think it's very similar to a hierarchical Bayesian model. Actually, you may not be wrong. So technically, I'm trying to do a regression to fit a regression, but I know my parameters here, for example, slope and intercept, you're following a normal distribution, which the mean is this black line, but it has a variance around it. And actually, even the Poisson models that I explained, like a negative binomial, they are also a hierarchical model. And Bayesian models in general, they can be very useful. So you can have an assumptions for the prior and try to predict the parameters in the model, to adjust the parameters in the model. The main challenge in Bayesian models is your assumptions about the prior. So if your assumption is good, it can be based on the previous data, it can be based on the other studies, it can be based on the engineering judgment or expert suggestion. But if you're not choosing the prior well, it may cause problems in the predictions. And they can be useful when there is not enough data, or you need more flexibility in the prediction. And apart from all these statistical methods, they were very useful before. By more computational resources becoming available, by more data becoming available, it gives us the chance to use more complex models. Tree and random forest models, they are one of the most useful ones, and particularly random forest because it's less susceptible to overfitting and more generalizable. Then we have support vector machine for particular classification. We have neural networks model. Various type of neural networks model have been used during the last 10 years, including LSTM, CNN models, autoencoders. They have been used for detection of the incidents in particular. Bayesian neural networks, GNN recently for traffic prediction, but we've seen a few research papers that they're trying to use that for incident prediction, and the other type of neural networks. As I said, they are very powerful and flexible, but the user, the designer should be very cautious about the overfitting because these models are very flexible. So overfitting may happen. And also they require a big sample of data. So if you have, for example, 6 months of data, not many accidents in it, probably these methods can be very challenging to be used. You need a good amount of data for that. And then we have the survival models, which they are using another approach. So the main idea of survival models is trying to predict the inter-arrival time of accidents, which is something that we usually see in the reliability community. You're trying to predict the time rather than the frequency. even though at the end you can always convert them to each other, but the general idea is different, and the distribution that we usually assume is different compared to previous methods that I discussed. But still, this one is a family of GLM models again, and we usually assume extreme value distribution for the error. And there is one new approach that I have seen in the last maybe 3 or 4 years is being used, is the model stacking. So the main idea is, so we have ensemble methods that they use multiple train models or multiple train methods to improve the prediction. So the simplest one is I have, for example, 10 different models, and I take the average of their prediction. Something similar to what random forests do. But what if I become more expert, like more complex, and I use another machine learning method on top of 10 other machine learning methods and use their prediction to predict one more, and to add one more layer to my prediction. This can be considered as one level more advanced than the data mining method. But again, they are very flexible, so the user should be aware of overfitting. They have to do a lot of training and testing to make sure the data is not overfit, that the prediction is not overfit, the model is not overfit. And because of that, you need a lot of data. And again, this one is gaining more popularity because the available data is becoming bigger and bigger. And also the computational power is becoming more affordable. I talk about the models. Let's briefly talk about some of the features and the feature selection. As all we know, the performance of the model highly depends on the input of the data and the feature that you want to use. Adding too many features, add too much flexibility to the model, which may cause overfitting, and also it will increase the computational time, which we are reluctant to do that. And also not having the relevant information, it will compromise the accuracy of the model. The features themselves, there are different type of categorization for it. Usually people do like temporal, spatial, and a spatial temporal. So temporal or the features, they depends on time, like time of the day, or for example, weekend, they may have fewer number of accidents compared to during the week. Then we have the spatial features, like the features usually regarding the roadway segments, they are not changing over the time. And depends how you define like the time. So they may change over 20 years, but they may not change over 1 year. And then we have spatial temporal data, like for example, weather data or traffic congestion. And again, the weather data, it depends the scale that you're looking at the problem. So in the scale of a state, the weather data is a spatial temporal, but in a weather of like a city, it might be just temporal. There's another type of categorization. So people can sometimes use a static or dynamic. So which means is if the features are changing over the time or not. For the temporal features, I briefly mentioned it, but the weather data has been used a lot. And there are various research topics that they are trying to show if one specific feature is important or not. But it really depends on the location of the problem, the time of the problem. So if you're focused on highways, you may get different results than if you're focused on for example, study in a city. So some research papers, they showed visibility can be important. Some of them actually, they showed it's not very crucial factor. But in general, visibility, precipitation, temperature, these are the most important factors from the weather. Seasonality also can be important. So during the summer, some roads, they may get more traffic flow. So then they might be more dangerous. As I discussed, the weekend or not can be important. The time of the day can be important. So again, depends. Sometimes traffic congestion increase the chance of incident, but also it has been shown that traffic congestion, they reduce the severity of the accident. And it's kind of intuitive, right? So when the cars are driving slower, so a dangerous accident, the chance of a dangerous accident, a high intensity accident might be lower. Or already discussed like the weekend or not, but holidays can be important. An event in the center of the city can totally change the traffic pattern. We have spatial features. So the most important one, I think, is the traffic flow. So if you have more cars on the street, statistically, there's more chance of accident. And AADT is technically showing how many cars are going through this specific roadway segment. Again, the length of the segment is again intuitive. If a segment is longer, the chance of an accident on it is higher. The length is again the same. And apart from that, there are some social economical factors. So actually, there are a couple of studies. They show a region with more density of bars, there are more density of hit and run accidents. And these are also some other type of the features they can be considered. And then we have spatial temporal features. The most important one is the historical data. Historical data can give us the most amount of information for the future. If a segment is historically dangerous, most likely in the future is also will be dangerous. The average speed of the car, so or congestion or traffic features can also be important. And also in particular for the severity, the incident, the speed is important. And so usually you collect, so the time resolution of the data is different. Usually incidents are collected continuously, so you know the exact timestamp of the incident. But for example, weather data, usually you collect it hourly or sometimes daily. And at the end, it may cause some problems. So the main problems regarding the feature selection is first one is unobserved heterogeneity. If you're not features that are not recorded, but they are playing an important role in the incident, if you don't take them into account, it may compromise the accuracy of the model. Sometimes there are some, so sometimes the relationship between the features and the results, it's not very clear, so you don't know which one is causing the other one. The classic example of it is the ice warning signs. So usually you put the ice warning signs in the location that the records are showing the high rate of accidents. But if you study, if you're not very careful, so you may get another conclusion that is ice warning signs, you're increasing the chance of incidents. The data can be biased. So a very good example of it is usually small crashes or maybe bumper to bumper crashes, they are not getting reported. So usually the data is a little bit biased towards heavier and more severe accidents. And aggregation, so assume you have a data for temperature or precipitation data for a day, but it's not telling you the distribution of it for a day, because when you're aggregating for a long range, you usually consider the data is uniform and you're not considering the peaks or in the data. So that might be another reason that your data might not be accurate and helpful, because of the aggregation, because of the big time range or space range for the aggregation. For the feature selections, so this is the main categorization of the feature selection. So we have filter-based method. So for example, it's very common, you calculate the correlation between the input and the output, and if it's not showing anything, you don't want to use them, or the variance of the data. We have chi-square, which is useful for the categorical data. F-score is showing the entropy based on the predictors and what we want to predict. Mutual information is also very helpful and informative. There are other methods that you're trying to combine some of these methods and for filter to filter the features, to narrow them down. Then we have the wrapper methods that for example, forward selection and backward selection using BIC or AIC. That might be the most famous ones. Then we have the regularizer. So lasso, ridge, and elastic net, they are the most common ones. And also tree models, they give you feature importance as well. And so they're more than this, but I think these are the most important ones that can be used for the feature selection. But also you need the expert's knowledge for that. You cannot just blindly go through these methods and choose your features. We also have a review paper, so which is trying to summarize this process, the whole pipeline that I briefly mentioned more in detail. So if you're interested, for now it's available on arXiv. You can go through that for more details. I think this is my last slide. I made some room for Ayan to talk about some robustness in the prediction. But if there is any questions, feel free to type in chat or just unmute yourself and ask.